Imagine a rocket that could cut the journey to Mars by months, opening up the solar system for human exploration, asteroid mining, and even permanent moon bases. Now imagine that rocket's engine is powered not by chemical explosions, but by the splitting of atoms, an engineering feat so powerful that even its failures could shape the future of space travel. This isn't science fiction. It's happening in labs and test facilities across the US, Russia, and a handful of other countries right now. At the center of it all, nuclear thermal propulsion, or NTP, a technology that, for decades, has promised to blow past the limits of chemical rockets. But there's a catch. For every breakthrough, new problems emerge: technical, political, and even existential. Will this new age dawn, or will humanity's boldest dreams explode on the launch pad? Let's start at the beginning. Rockets, for all their fiery spectacle, are basically flying fuel tanks. The Saturn V, the legendary rocket that sent Apollo astronauts to the moon, had to burn through 3 massive stages just to break free from Earth's gravity. At the heart of every chemical rocket is a fundamental trade-off. The more payload you want to carry, the more fuel you need, and the more fuel you need, the heavier your rocket becomes. It's a relentless, almost cruel cycle known as the tyranny of the rocket equation. For decades, engineers have chipped away at these limitations with smarter designs and lighter materials. But there's a hard ceiling. Chemical rockets can only get so efficient. Their engines, their specific impulse in technical terms, maxes out around 450 seconds for the best liquid hydrogen models. After that, returns diminish. No amount of clever tinkering can change the laws of chemistry. Enter nuclear thermal propulsion. Instead of relying on a chemical reaction, NTP uses a fission reactor, a controlled nuclear chain reaction, to superheat hydrogen gas, which is then blasted through a nozzle to produce thrust. The result? Specific impulses of 900 seconds or more, double or even triple what chemical rockets can achieve. That's not just a technical detail. It means bigger payloads, faster trips, and way more flexibility for deep space adventures. NASA's Doyce Sonny Mitchell describes it bluntly. NTP advanced systems could provide far faster transit times to Mars, enhancing mission robustness and enabling more ambitious exploration. But why, if the technology is so promising, aren't we already streaking to Mars on nuclear wings? The answer lies in the tangled history of NTP. The roots stretch back to the 1950s and the fevered competition of the space race. The United States and the Soviet Union both experimented with nuclear rocket engines, most famously through America's NERVA, Nuclear Engine for Rocket Vehicle Application program. At its peak, NERVA demonstrated staggering power, over 4 million kilowatts, enough to dwarf the output of an entire small city. Engineers ran successful ground tests, and by the early 1970s, many believed a nuclear rocket to Mars was just around the corner. But then, in a twist worthy of Cold War drama, politics intervened, budgets tightened, public fears over nuclear accidents grew, never mind the technical hurdles of launching radioactive material into orbit. When the Apollo missions ended, so did NERVA. The dream sputtered out. For decades, chemical rockets carried the torch. Meanwhile, nuclear propulsion became the stuff of science fiction novels and classified military projects. But the vision never truly died. As Martian ambitions roared back in the 21st century, and as private space companies began to eye asteroid mining and lunar settlements, the old promises of NTP looked relevant, even urgent once again. Fast forward to today, the game has changed. NASA and DARPA, the Defense Advanced Research Projects Agency, are pouring resources into the Draco program, a new effort to finally test a nuclear rocket in space by 2027. This isn't the only push either. Private players like Pulsar Fusion are racing to test fusion-powered engines by the end of the decade. Test facilities like NTREES, CF-EAT, and the TREAT reactor have been upgraded to put fuel samples and core components through stresses that mimic the violence of launch and deep space travel. But NTP isn't just one idea. It's a bustling field full of competing concepts and fierce debates. One technology getting attention is the centrifugal nuclear thermal rocket, or CNTR. Developed by researchers at the University of Alabama at Huntsville and the Ohio State University, CNTR aims to nearly double the specific impulse of traditional NTP systems, pushing it to a staggering 1,500 seconds. For context, most chemical rockets top out at 450 seconds. Traditional NTP gets maybe 900. CNTR? 1,500. That's a leap so dramatic it could fundamentally redraw the blueprint for human exploration. Here's how CNTR works. Instead of using solid uranium fuel rods, it uses liquid uranium, kept molten by spinning it at incredible speeds like a centrifuge inside the reactor. Hydrogen gas is bubbled through this radioactive whirlpool, absorbing heat at a terrifying rate, and then shot out the back as high-speed exhaust. The result is jaw-dropping efficiency, more than enough thrust for heavy crewed ships or massive cargo haulers. Theoretically, it means supplies and astronauts could reach Mars in a fraction of the time, with emergency return options and bigger, safer habitats. These aren't just engineering upgrades, they're mission-changing capabilities. No wonder NASA Administrator Bill Nelson is enthusiastic. Nuclear thermal propulsion offers the potential for faster journeys to deep space, a critical capability for crewed missions to Mars. But as the saying goes, the devil is in the details, and with CNTR there are a lot of devils. A recent paper in Acta Astronautica lays out 10 major engineering challenges stalling CNTR's leap from laboratory to launch pad. Let's break them down and feel the weight of each one. First, handling liquid uranium at temperatures of several thousand degrees Celsius, while keeping it from vaporizing or escaping containment. That's a materials science nightmare. Any breach or chemical reaction can turn a rocket into a dirty bomb or a multi-billion-dollar toxic spill in space. Second, the need to spin the molten uranium at insane speeds to mimic gravity and keep it stable, all while a spacecraft is accelerating, vibrating, and enduring the stresses of launch and cosmic radiation. Any error in this dynamic ballet could spell disaster. Third, the interaction between superheated hydrogen and its radioactive bath is barely understood, especially when you add high-speed bubbles and shockwaves into the mix. Hydrogen atoms smashing through the molten fuel, picking up neutrons and isotopes, creating unpredictable radioactive byproducts. Is this stable or a ticking time bomb? The Draco team and university researchers have zoomed in on 4 particularly nasty problems. One stands out: uranium vaporization. If too much uranium turns to gas, not only does the engine lose efficiency, but radioactive material could leak into space, violating international treaties and public trust. The researchers are now developing new coatings, exotic blends of advanced ceramics and metals, to try and contain the uranium, but so far, no material is perfect. Another problem: the hydrogen bubbles. In a working CNTR engine, hydrogen must be channeled through the swirling liquid uranium, capturing energy and exiting at blistering speeds. But those bubbles are nearly impossible to model. Turbulence, temperature shocks, and the Coriolis effect caused by the centrifugal force could destabilize the entire fuel mass. To get a handle on this, researchers have built experimental setups called Ant Farm, a static model, and Blender 2, a rotating model with X-ray imaging. Instead of uranium, they use Galinstan, a non-radioactive liquid metal, and nitrogen as a stand-in for hydrogen. But so far, the mathematical models haven't nailed down exactly how bubbles move in these extreme conditions. Without reliable numbers, designing a safe, efficient, full-scale engine is like trying to run before you know how to walk. Then there's the matter of the fission reaction itself. Keeping the temperature and neutron flux stable requires adding elements like erbium-167 to the reactor, but that, unintentionally, creates other chemical byproducts, like xenon and samarium, which can poison the nuclear reaction, reducing its efficiency or even shutting it down. If these gases aren't removed quickly and efficiently, the rocket risks stalling mid-flight, leaving astronauts stranded or worse. All these design challenges are compounded by the realities of space travel. A nuclear rocket must start cold, survive the rigors of launch, then fire up only when safely far from Earth's atmosphere, making remote operation and reliability absolutely critical. Even if the technical puzzles are solved, public fears and regulatory hurdles loom large. Launching a nuclear reactor atop a rocket always invites controversy. International treaties strictly limit what countries can do in orbit with fissile material. A single accident could set back humanity's space ambitions for a generation, or worse. Yet the rewards are just as monumental. Master NTP and Mars becomes a stepping stone instead of a distant dream. Asteroid mining becomes economically viable. A permanent presence on the moon, sustained by abundant cargo and energy, becomes reality. Not surprisingly, governments and private companies are investing millions to crack the code. As Michael Houts of NASA puts it, recent advances in materials technology may provide a more affordable pathway to developing a nuclear rocket engine, making NTP more accessible. But can scientists and engineers overcome the technical, political, and psychological barriers fast enough? The Draco program has set an ambitious target, an experimental flight by 2027. But even the most optimistic supporters admit that the path ahead is packed with risk. The fate of NTP, and perhaps our entire space future, hangs in the balance. So, what unfolds next, as teams race to balance innovation against physics and vision against safety? Will humanity's nuclear rocket revolution finally blast off, or will we be left once again on the launch pad, staring at the stars and asking, did we aim too high? Every leap forward in technology is a collision between our wildest dreams and stubborn reality. Nowhere is this truer than in the race to perfect centrifugal nuclear thermal rockets. So, what happens next? How does the future unfold if we crack the code, or if we fail? Let's look at the possible worlds ahead. If the technical challenges are met, and let's be clear, that's a series of ifs stacked higher than a Saturn V, then the implications are profound. Right now, even the most optimistic Mars mission plans require astronauts to spend up to 9 months in transit. That's 9 months battered by cosmic radiation, cut off from real-time help, and gambling on everything from food supply to crew morale. Nuclear thermal propulsion, especially in its centrifugal form, could slash that journey by as much as 25%, possibly even more as the technology matures. Picture this: a crewed mission to Mars that takes just 6 months, maybe even less. The window of opportunity for complex human exploration, in orbit, on the ground, and on the return journey, widens. Astronauts spend less time exposed to space hazards, and the entire operation becomes less risky, less expensive, and far more flexible. NASA's Richard Ballard summed it up best. An NTP system could reduce crew transit time to Mars and increase mission flexibility, providing greater mission control and safety. But it doesn't stop at Mars. With higher specific impulse, a CNTR system could let us reach the outer planets, not just in our lifetimes, but possibly our careers. Missions to icy moons like Europa or Titan, ambitious asteroid capture projects, even lunar bases that don't have to wait for chemical resupply, all of these move from science fiction to the edge of the probable. There's also a potent economic dimension. Rex Gevedin of BWXT points out, it is an opportune time to pivot our capabilities into the space market, where we see long-term growth opportunities in nuclear propulsion, driving innovation and economic benefits. We're not just talking about exploration, we're talking about a whole new space economy. Faster, more frequent cargo runs, space tourism with reasonable schedules, the first truly global satellite internet. Even asteroid mining becomes more enticing when you can bring resources back faster and cheaper. But, and it's a big but, none of this is possible if we don't solve the engineering and political puzzles standing in the way. The technical issues, as we saw, are daunting. The CNTR, with its molten uranium, presents problems that have never been solved. Containing and controlling liquid uranium in a spinning superhot centrifuge, modeling hydrogen bubble behavior, dealing with radioactive byproducts like xenon and samarium that can poison reactor performance, developing coatings that can survive the unholy marriage of heat, fission, and chemical stress for years at a time. And that's before we touch the tangle of regulatory, ethical, and geopolitical hurdles. Nuclear technology in space is fraught territory. Current treaties, including the Outer Space Treaty of 1967, limit the deployment of weaponized or uncontained nuclear material beyond Earth. Even peaceful nuclear propulsion faces scrutiny over launch safety, radioactive contamination in the event of failure, and long-term stewardship of spent engines. Public opinion, too, fluctuates between excitement and dread. The specter of a nuclear disaster, however unlikely, haunts every public announcement. Policies shift accordingly, threatening to derail programs at the whim of political winds. DARPA's director Stephanie Tompkins put it starkly. Advancing space technology through the Draco program is essential for efficiently transporting materials to the moon and people to Mars. But efficiency is only as good as society's willingness to accept the risks and trust the science. Let's not forget international competition. The United States is not the only country eyeing nuclear rockets. Russia, China, and new space players are investing heavily. In the past, Cold War rivalry drove the Apollo program. If CNTR technology is seen as the next strategic high ground, we could see a new kind of space race, one centered on propulsion rather than destination. That could accelerate development but also stoke fears, secrecy, and possibly even confrontation. Yet, there's an intriguing upside hidden in the details. Regulatory and engineering hurdles, while formidable, are not insurmountable. In fact, we already have the blueprint from past breakthroughs. Look back at the dawn of aviation. When the Wright brothers first took to the sky, naysayers cited risks and technical dead ends. Today, air travel is one of the safest ways to move around our planet. We learned, adapted, and regulated until the unimaginable became routine. NASA Administrator Bill Nelson is optimistic. Nuclear thermal propulsion offers the potential for faster journeys to deep space, a critical capability for crewed missions to Mars. His words echo the sentiment of pioneers everywhere, cautious but hopeful. Achievement is a function of both imagination and perseverance. So, what lessons can we draw from all this? First, the practical benefit for you, the viewer, is not just about rockets or Mars. It's about understanding how transformative technologies challenge our thinking, about risk, progress, and what's possible. The development of nuclear propulsion is a microcosm of technological advancement itself. It's messy, uncertain, and sometimes controversial. But it's also the story of every great leap humanity has made. Each step forward, whether it's flight, nuclear power, or the smartphone in your pocket, was once considered too risky, too complicated, or just impossible. If you're thinking about your own career, education, or investments, the CNTR story holds another lesson. The future belongs to those who can grapple with hard problems, navigate uncertainty, and keep asking, what's next? The people working on these engines are experimenting with new materials, combining computer models with hands-on testing, and blending disciplines in wild new ways. Whether or not you ever work on a rocket, the mindset they're embracing, of relentless curiosity and rigorous problem-solving, will shape every field in the coming decade. And keep in mind, public perception and political engagement matter. Advocates, voters, and inquisitive minds can steer the conversation. If enough people understand the real costs and benefits, and push for smart regulation, not just knee-jerk fear, we get better outcomes, not just in space, but in every technology that's on the frontier. So, what's the bottom line? Can the engineering and political challenges be overcome in time for this next leap in space travel? The answer, while not simple, is a resounding yes, if. Yes, if we commit the resources. Yes, if we keep pushing through the setbacks. Yes, if we bring along the public with transparency, dialogue, and a shared vision. History shows that when those conditions are met, the impossible bends toward reality. But if we stall, if we let fear or inertia win, then the next chapter of human exploration could close before it's even written. The clock is ticking. DARPA's Draco demo is scheduled for as soon as 2027. The next few years are a crucible, not just for engineers and astronauts, but for everyone who dares to imagine a wider horizon. Let me leave you with one last little-known fact: the secret weapon in the nuclear propulsion race. Many of the materials and modeling techniques developed for these engines are already finding applications in medical imaging, advanced manufacturing, and even clean energy here on Earth. Even if CNTR never flies, the ripples of today's innovation could benefit all of us in ways we haven't foreseen. So, what can you do? Stay curious, follow the research, support responsible exploration. And if you're inspired, get involved, whether that means studying engineering, joining policy discussions, or simply spreading the word about what's really at stake. The battle for the stars isn't just fought with rockets. It's waged with ideas, votes, and visions. The future of space travel, of humanity's place in the universe, is not a spectator sport. Where will you stand when the countdown begins? Thanks for watching. If this journey fired up your imagination,